In this video, we are going to deal with the formation of the DFT from DTFT. The frequency domain representation of a discrete time signal obtained using discrete time Fourier transform, that is DTFT, will be a continuous and periodic function of omega with periodicity of 2 pi. This is explained earlier, and we have also shown that we have obtained the spectrum, the phase spectrum and the magnitude spectrum, and this have a period of 2 pi. And also it is said that to obtain the discrete functions of omega, that is to obtain the DFT from this DTFT, we have to obtain samples at a sufficient number of frequency intervals. So in the previous part also we have considered that the period is given by 2 pi, and we are taking n number of samples from this spectrum, or the x of e raised to j omega obtained. N number of points are obtained. So the sampling interval is given by 2 pi by n. 2 pi by n. Thus let x of e raised to j omega, let x of e raised to j omega be the discrete time Fourier transform of the discrete time signal x of n. And the discrete Fourier transform of this x of n, the discrete Fourier transform of x of n is obtained by sampling one period of the discrete time Fourier transform at a finite number of frequency points. Thus we have to sample this discrete time Fourier transform x of e raised to j omega at a finite number of sampling points for obtaining the DFT. Okay, thus we have obtained the n number of sampling points, and we have we have taken the n number of samples at a period of 2 pi, and the sampling interval is given by 2 pi by n. Then the sampling frequency points are denoted by omega k, and the sampling frequency points are denoted by omega k. And after sampling, we have to obtain the sampling frequency point. Thus a sampling frequency point which is represented by omega k, and the omega k, the sampling frequency point, is given by omega k, which is equal to 2 pi by n, which is a sampling frequency into k. Thus we have to get the kth sampling frequency point, we have to multiply the interval, that is a sampling frequency is a sampling interval, into k, so that we will get the kth sampling frequency point. So omega, the sampling frequency point which is given by omega k, is equal to 2 pi by n into k, and k is equal to 0, 1, 2, 3 etc. up to n minus 1. We have considered up to the points up to n minus 1, that is we have not included this 2 pi because the value of the 2 pi, the value at 2 pi is same as that of omega is equal to 0. So we have not included this k is equal to n minus 1, and we have only considered the points, the sampling frequency points from 0 to n minus 1. And by simply substituting this in this omega k, the value of omega k, in our equation of x of e raised to j omega, then we will get the equation of DFT, that is we have considered this this part, that is the sampling frequency points are denoted by omega k, that is omega k is equal to 2 pi by n for k is equal to 0, 1, 2, 3 etc. up to n minus 1. And now the DFT is a sequence consisting of n samples of DTFT, that is for the above part we are taking n samples. So if we take n samples, then the DFT is called n point DFT, and the n-point DFT means the n samples of the DTFT, similar to the DTFT x of e raised to j omega, which that is the DTFT of x of n. We are taking n samples corresponding to that. So now the DFT is a sequence consisting of n samples of DTFT. I think you have got the idea of what this explains. Let the sample are denoted by, let the samples denoted by x of k for k is equal to 0, 1, 2, etc. up to n minus 1. Therefore, the sampling frequency, the sampling of x of e raised to j omega is mathematically expressed as x of k, that is the samples, the required samples, that is the DFT. This explains the DFT of the discrete time signal x of n, which is equal to the DTFT of the same signal which is sampled, the DTFT of the same signal which is sampled at omega is equal to 2 pi by n into k. So this explains, or this explains that the DFT, that is x of k, is the samples of the DTFT of x of n, where the sampling is done at a sampling interval of 2 pi by n, and the sampling frequency points are given by omega is equal to 2 pi by n into k. So by replacing the equation of omega is equal to 2 pi by n into k in the equation of the DTFT, we will get the equation of DFT, that is the samples, that is a discrete time, the discrete time signals are converted to, the discrete time signals are converted to discrete frequency domain signals, discrete frequency domain periodic signals by the DFT. Thus we can simply say the DFT are the samples of, or the discrete form of the DTFT, where the sampling is done at a rate of 2 pi by n, and the sampling frequency points are given by 2 pi by n into k. Thus this explains the DFT pair, where the DFT pair is known as the DFT, that is the x of k, the DFT, the samples, these are the samples, that is DFT of x of n, a discrete time domain, a discrete signal which is in time domain is converted to corresponding frequency domain signal, corresponding frequency domain discrete signal by the DFT, and the discrete frequency domain signal which is given by x of k, which is obtained by using the equation. Here we can see the, instead of the omega, we have replaced 2 pi by n into k, and so we have got this equation, and this equation is formed from the DTFT equation, and k is from 0 to n minus 1, and the IDFT, inverse DFT, for obtaining the discrete time signal back from the DFT is 1 by n sigma k is equal to 0 to n minus 1 x of k e raised to j 2 pi by n into k into n, for n is equal to 0 to n minus 1. By doing this operation, we will get the signal x of n, the discrete time signal, back from the DFT x of k, and we have defined the term, this term as omega n, which is equal to e raised to minus j 2 pi by n, and this term have a particular name which is called twiddle factor or phase factor, because this factor is the one which controls the phase of the DFT. As I have told before, this e raised to minus j 2 pi by n is the factor which controls the phase of the DFT. So it is also called twiddle factor or phase factor, which have some properties which will be explained later, and the integer n, which is called the time index, and the integer k, which is called the frequency index, because by using this k we will get the sampling frequency points.